This is the Inspire Around the Globe conference. This conference will be recorded. And I'm Krina from Team RoSophia. It's 1455. And I guess we can start. Who wants to start presenting?
I'm going to share right now. Okay, screen should be visible.
Yes.
Can we start whenever we're ready?
Yes, you can start.
Hello, everyone. We are FTC 23511, the Seattle Solvers, and today we're going to be talking about how to tackle complex designs through planning, specifically our multi-chassis and our swerve. I'm Ajay, and I'm our finance lead.
I'm
Socket. I'm Socket, and I'm our design lead.
I'm Ishan, I'm our outreach lead.
And I'm Arash, I'm our software lead.
Okay, so a little bit about who we are. We are a fifth-year first team, and this is our third year in FTC. Last year, we had a top 6% OPR in Into the Deep, and this year, as of now, we have a top 4% OPR. We are an open alliance team, meaning all our CAD and code is public to anyone who wants to see it. And we compete in Washington, meaning our first competition is in early November, which gives us only about 2 months after kickoff to really get our robot into function. And competitions after that are about every 2 weeks. So last season, we decided to have a full robot rebuild between our interleague competition and our state championships. And we wanted to add a level 3 hang, but that was too overambitious and failed. As you can see, our OPR dropped from at interleagues from 134.48 to 120, showing that complexity in our design actually made our robot perform worse in the long run.
So going into this season, we made a lot of changes right from the off season. So in our planning, we are using the off season to essentially try out as many new mechanisms and learn as much as possible, which we mainly did through just building as many robots as we could over the off season. So on the right, you can see that's a turret mechanism we actually built over the off season for a wiffle ball shooter that Ishan will talk a little bit about later, and also a completely new robot for the Into the Deep season, which used carbon fiber, a power takeoff mechanism, and basically a lot of things that we wanted to try out, but we couldn't. And this planning change really helped us because we're able to try out these mechanisms in a low risk setting, and then we're able to better implement them in season, as we did with Swerve, which we'll talk about. Other thing with hardware is we really tried to make our mechanisms as modular as possible, so that we could be able to iterate on them without doing a complete rebuild. So Ajay mentioned we did a full rebuild from interleagues to states last year, which was almost like less than a month. And we found that redoing everything from scratch actually took a lot of time, and it wasn't as efficient because we were only making minor upgrades. So this year we tried to make our mechanisms mounted in a way such that from the very beginning, we're able to quickly take them off, improve them, and then reattach them on to save as much time during season. And then Ars can talk a little bit about the software changes we also made.
So on the software, one of the biggest things that we did is we integrated full swerve support and control into our open source library solvers live. This includes the kinematics, the controller that actually handles the movement, and a simple visualizer for easily creating paths, more of which we will be talking about.
So one of the major projects we took on this off-season was making a multi-chassis. With focus on modularity in mind, this chassis has about 75 different mounting holes throughout. You can see like some of them, especially on this back plate here. It has 4 different configurations for our hub mounts from some just on this side, like from all of them on one side to what you see here with one on either side. There's 3 different places for mounting odometry. Though we use like 2 wheel with pinpoint, it allows us to have some extra like uh, it allows us to like essentially mount the wheels in a way that this robot can work for any design. The point of this multi-chassis is essentially to function for any different archetype of robot. It can function as a swerve drivetrain or a mechanism. And it's kind of similar to the strafer chassis in that way where you can put essentially anything on it, you can turn it into absolutely anything, and this robot can work for basically any season. So the reason we did this in the off season was essentially to limit the amount of time we need to work on our robot during the season. We don't have to design a drivetrain if we have one that works for essentially every season, like built in the off season. So that was one thing we made. So I'm actually going to go give a bit of a CAD walkthrough on this one here. So first, let's start with the actual drivetrain here. So you can kind of see this is the multi-chassis here I was talking about. This one has like swerve modules in it. You can see on the bottom, like I was talking about earlier, you have those three odometry mounting points. These cutouts for swerve module, which you can use either mechanism wheels or swerve on. Um, yeah, so there's all these different mounting holes throughout the robot. You can see so many of them here. You have all these extra like random holes for bearings, all these screw holes, right? You can see these are actually motor mounting points here, right? So we have like over 75 of those throughout this robot here, just to allow us to mount basically anything anywhere, which as Socket was saying last year we had to rebuild our entire robot just to make minor changes to it. To add like a L3, we had to build the entire robot again from scratch. With this robot, all these mounting holes, we don't have to go do that because we can essentially make any change to this robot. We can move things around. We don't like need to worry about recutting new plates or anything like that. So it's kind of like a strafer chassis, except you're getting all the benefits of a parallel plate drivetrain and the custom like weight savings and everything in this drivetrain here. So best of both worlds. So we're going to go into a bit on how we like planned out something like this. So this is a master sketch here. For those of you who don't know what a master sketch is, it's essentially a series of sketches here that allow us to essentially plan out our robot without building it like physically or without having to go through and design the full thing. Do this before like making the robot. It allows you to plan out where you're going to put every single item here. So you'll see like we have a bunch for our drivetrain here. You'll see like lots of different you'll see lots of different pulleys throughout, right? So like you can essentially mount anything here, right? These are all like major points we could find for different archetypes. So on the side you'll see we have like turret, shooters, like slide archetypes. So like last year the main one was two slide archetype and into the deep, right? That was what we used in our robot. And like you can see here, we kind of planned for that even with our like robot this year. We want to make it able to function for that. So we added like all these different like bearing holes for pulleys and things if we ever have to make a robot like that, right? So you can see here, I'm going to go open up the plate so you can see kind of how it affected it. Uh, so you can see here, these are the vertical slide mounting holes right here. This entire top lip of this plate is just to like account for the vertical slides here. And same thing for these holes on the bottom, right? Or these this like line of vertical holes. That's all just for vertical or for horizontal slides right here. You can essentially mount a 14-inch BWT link slide. Those are what we use on our robot, but you can use them like you can essentially make a two-slide archetype on here, or you can do something like a like turret and a, a turret and like shooter kind of one. So this off season we actually tried to develop a wiffle ball shooter robot. So you can see here like active intake and everything all mounted on the same chassis, right? So general idea where you can mount essentially anything on here, right? So the idea of one of the other things we focused on, like I said earlier, was mechanism versus swerve. So in the planning, we actually had to involve like a lot of different options for it. If you want a chassis that can be used anywhere, you're going to need it to basically have a lot of different contingencies or possibilities for design. So one thing you'll see is we have three separate mounting options for mechanism in case like depending on what the robot needs to do or what else we want to put on the robot that might take up the same space. You have these essentially like center mounted motors here. Then you have all these like you can have them mounted even like higher here where you have two stages of pulleys, right? Or you can even like go through a singular stage of gears. You have all these different options made because you want this chassis to be essentially as modular as possible. So like we can essentially build anything on this, but so that was kind of the main focus here, modularity, which this robot is kind of like this drivetrain is essentially something you can turn into absolutely anything, any type of archetype, any type of robot. So now Socket's going to tell you a bit about more about like the swerve. Yes.
Yeah, I'm gonna share my screen to take over. Just
Okay.
a little bit before the swerve, Arsh is gonna talk a little bit about the software planning that also went into our change. So yeah, Arsh.
Yeah. So one of the biggest things that our team did in order to make our swerve successful on the software was working on our code without a robot. There's actually a surprisingly large amount of things that you can do without a robot to help you make sure that you can complete your tasks effectively. And this is really important, especially for us, because Washington is a very tight deadline. So especially after the first competition, you're going to have competitions coming out nonstop every 2 to 3 weeks. So one large factor contributing to our success in early league meets is that we actually theory coded a lot of our systems early while our robot was still being built. One thing that we did was our launcher math. So this is getting the velocity from the distance of the robot and other similar things for our turret and our intake. This is also including structure for our files, as you can see in the bottom right corner, which is effectively creating folders and directories and entries to help organize our code. This can all be done with our robot. Additionally, uh, teams can also learn about libraries. This is things like popular pathing libraries like Pedro Pathing or Roadrunner, or command-based libraries like our very own solverslib or alternatives like Next FTC and Mercurial. And then teams can also integrate them with each other and also create autonomous paths with visualizers uh, before just to make sure their team has enough time to actually test out everything.
Yep. So moving on to specifically Swerve, like how we were able to implement a complex mechanism. So there's going to be an overview of what we did with Swerve. So firstly, if you don't know what Swerve is essentially four different high traction wheels that are able to rotate in any direction, and essentially they give you increased traction and movement speed in all directions compared to Mechnum, which can be efficient while strafing or moving diagonally. And we really wanted to try it out because it would be potentially useful across seasons. It wouldn't be just used in one season, but theoretically you could use it every year, just like how teams use Magnum every year. But however, it does come with a lot of difficulties because you are running 4 extra servos and sensors for figuring out where the wheels are actually facing. And all of these need to be operating efficiently all the time in both hardware and software. So in hardware, this means your power transmissions need to be efficient, so you're not pulling too much power. And also in software, you need to make sure you have good loop times, which Arsh will talk a little bit about how we optimize so that we have precise control over where the wheels are facing. So all of this, all in all, adds a lot of complexity for just having the basic functionality for your drivetrain moving. So it took us a lot of time to actually make this possible. So we actually spent our 2024 off season developing our Swerve drive, but we saw that it had issues with power draw, with accuracy, with also in software as well, that we weren't happy enough to use it in season. So we revisited it this off season. And then finally, we came up with the modules that we're currently using. And even then, they're still not perfected, and we still have things to improve on. So having these fallbacks, like in the multi chassis, like Ishan said, are really important because if for other reasons Swerve doesn't work out, we always have the option to return to Mechnum and at least have a functional robot, so we don't end up having a worse competition season because of Swerve. So, like Ishan did with the multi chassis, I'm going to talk a little bit about our 2025 Swerve module. I'm not going to go too much into our 2024 module, even though it is public. But the 2025 module, you can see it's slightly bigger, but you can see it has a lot less screws and nuts, which is something we really tried to focus on in trying to make our entire swerve a lot more modular and accessible. So Starting out with how we make this modular, we actually split up our entire server module into three different parts. So we start with the lowest level, which is the wheel. This is just a simple aluminum wheel with some tread on it, but you can see that it's modular within the next level, which is the pod. So by removing this screw and this screw, if we hide these two screws, in real life, you'd unscrew them. This entire axle over here and the wheel that's on it are basically able to slide out from the bottom. So we actually have a slot over here that allows you to just take this entire thing out the bottom. And we realized that using accessibility through the bottom of the robot was going to be very efficient because a lot of the times you have stuff on top of your server modules or on top of your mechanism wheels on your drivetrain. So, but there's not usually much happening below your robot. So we kind of made everything accessible from the bottom. This also means that not only do we have the wheels modular like that, these four screws, if you unscrew these four screws, then we're essentially able to take out everything on this bottom half. So everything over here is just able to slide out and we're able to access anything. So if we need to replace the tread, like tighten any screws, anything like that, we're able to have access to that. But it doesn't just stop there because we go further in the next step of the module. We're actually able to take out the entire pod, so that entire previous subassembly. If you loosen some set screws at the top and you remove these four screws, again, accessible through the bottom, just so that we have like full control over being able to remove things. So if we hide these four screws, there's actually nothing constraining the pod from just being slid out the bottom. And again, we're able to access anything. So if we want to grease the gears because we want higher efficiency, if we need to re-grease them, then we can through that. Or if you need to tighten any screws, again, inside here, it just makes it a lot easier to do all that. And then finally, at the highest level, this entire swerve module is designed as a module and not directly integrated into like a drivetrain, which has like one big plate, which has all four wheels and everything mounted onto it. Because we wanted it to be able to be replaced with these side mounting screw holes with these square beams. So this allows us to essentially unscrew the swerve modules entirely. So if we want to like completely replace the module and replace it with mechanism, or if it's just sometimes easier to access, for example, the servo over here, if you take out the entire module, we also have the ability to do that. So this just gave us a lot of control over the previous year, which had a lot of like different screws that made it hard to access. It was also more compact, so it was harder to reach in there and do this. So these were all improvements that we've made. But this isn't ending here. Because of this kind of modularity, we're actually able to improve our swerve even during mid-season. So currently we're planning to replace the treads that we currently have with a new molded tread. So you can see we're going to replace the wheel with a custom molded urethane tread. And this is possible because during the season, it's only going to take us maybe an hour to replace all four wheels because we can just unscrew these two screws, replace the wheel, and then pop it back in rather than having to design the entire swerve in a way such that you have to take everything out to access it. So this is something we're still doing in progress, and it's just one of the examples on how modularity can help you. Now Arsh will talk a little bit about the programming side of how we made swerve efficient as well.
Yeah. So the first thing that our team did when working on the swerve on the programming side was create the kinematics for it. So we started off by simply using Desmos to derive the kinematics with first order. However, we found out that these theoretical kinematics, when implemented in code, simply weren't enough. We had to optimize it. This is a really big issue because with Swerve, you have a whole motor a uh and a servo for each module. So you have a lot more hardware to deal with. So one of the some of the things that we use for optimizing our code is that we use something called slew rate limiting to handle gamepad inputs and make driving smoother, as well as determining when we should actually be turning the pod itself with the servo or actually setting a motor power. Then to actually control the swerve, we implemented a P2P, also known as a PID to point, which moves in simple straight lines. We didn't want to opt for more complex curved paths because they were going to take a longer time to develop, and this was something simpler that could easily be done in the off season, which would give us plenty of time to prepare for decode season. So the way this works is this uses a PID controller for the heading, another PID controller for the translational movement in order to accurately move the swerve drivetrain from one point to another point. And we found that this was all we really needed in order to get a consistent yet simple autonomous. Then for the visualizer, we simply modified the pedropathing visualizer instead of building our own one, which is also open source. And we simply added the functionality to only create lines and to adjust paths as needed. And then, like I said, because Swerve has both a motor and a servo, that has a lot more hardware reads and writes than you expect. So this is going to cause an issue with loop times because the longer your loop times are, that means effectively you're going to have more latency with your robot because you aren't getting the most up-to-date values from where your hardware actually is. So the first thing that we do is that we do some pretty simple things like bulk reads and motor caching, which effectively groups in all of your hardware reads together instead of calling them individually. And then motor caching and servo caching to some extent prevents unnecessary calls. Additionally, one more thing about necessary calls. One of the biggest things that our team strives to do on the logic side is making sure we don't have any unnecessary set power calls or any other logic things that we don't need to. We're only setting the power only when we absolutely must. This helps reduce unnecessary things even on a logic side, not just a hardware side, but this is a failsafe as well. The final thing we do for our loop times is implementing a library called Photon. This effectively is a little bit more complex, but it removes the global write lock. And what that on the global thread write lock. And what this allows us to do is this allows us to write faster to hardware, even if this comes at the issue of having a slightly less stable SDK. But this took a lot of time to perfect and making sure that it was stable. So this is definitely something if teams want to look forward to, that they should definitely spend a lot of time looking for a lot of investing into this, not something they should take with a very little time. And finally, we have Solver's Lib. Solver's Lib is our open source FTC lib fork that integrates all of these features together with the standard FTC lib features. This includes Swerve, this includes the loop time optimizations, and everything above that I just talked about. And this is critical for making our Swerve work. Yeah. Thank you
Yep.
for listening.
And thank you for listening. And if you have any questions, we can answer them here, or also you can go to the link tree and we have our contact information and our Discord server there.
Thank you for the presentation. If no one has any questions, I guess we can go to the next team. Mechamatis told me that they want to be next.
You can start presenting. Okay, so we are Team 19862 Mecha Mantises, and today we're going to be presenting our turret from the Into the Deep season for the Inspire Around the Globe conference presentation. So our team used the turret for the entirety of the Into the Deep season, from all the way to our first qualifier to our last official competition of the Maryland Tech Invitational. We were able to be the NorCal Winning Alliance captain and the Inspire 3 winners. We also competed at the first World Championship and the Maryland Tech Invitational, and we were also nominated for the Hardware Mastery Award at the Maryland Tech Invitational. We also ended the season with a maximum of 189 NPOPR. So these are just some pictures from our competitions. So we were also able to achieve, as you can see over here, the level 3 ascent with our turret, which is like a big part of like making our turret stable and making sure it's like robust enough to like lift our entire robot. And yeah. So now I'll be moving on to why we chose a turret. So what it allows us to do is have a full degree of freedom for picking up samples. So on the right over here, you can see a short video of our turret from the Into the Deep season. So What it allows us to do is like if there's like a large range of samples in front of our robot, we were able to turn and use our horizontal extension, which was also mounted on our turret, to effectively pick up the samples. We also had a Limelight 3A camera on our turret so that we had something called a hover mode where we could hover over a set of samples, and we had an algorithm that would allow us to choose which color depending on our alliance, and also prioritize like yellow samples compared to like blue and red samples, depending on what alliance we were and if we were doing samples or specimen. It also allows us to intake from both the front and back. So when we were doing samples, we would intake from the front so that we could deposit from the back to do samples. But when we were doing specimen, we would intake from the back and then deposit from the front so that we could also like intake again when doing specimen. And what else, and another benefit of having the turret last year was to have a fine adjustment without turning the robot during both outtake and intake. So many teams last year had a turret on, had a mini turret on both their intake and outtake, and this would require two separate mechanisms. But we could do both with just one like main mechanism turret on the on the base of our robot, so that we could turn while both intaking and outtaking. So there are two main types of turrets in general. Our team decided to go with the bearing stack turret, which, as you can see in this image, consists of 6 different bearings. And each of these are made in a bearing stack, which we'll go into more later. And another like alternative design that we were considering is a Lazy Susan turret, which consists of an off-the-shelf Lazy Susan, which you can mount on your robot and then mount other mechanisms on top and then like hold in this Lazy Susan into your turret. Overall, we chose the bearing stack turret like from the get-go because we thought it would be more robust and like easier to like maintain and service, since like each of the individual bearings could be replaced during the season. And we also found it easier to power with the pulley in the middle. Some like downsides to like the bearing stack turret is that it's really hard to get the tolerances right. So like the center hole over here, you need to have like very fine tolerances to like 0.1 or 0.2 mm, because otherwise you would have like a lot of like shake in your turret and it would like not turn as efficiently. And if the hole is too small, then you're gonna have a lot of friction while turning. So that's just one of the downsides, but we went through many iterations to get our tolerances right on our turret. And then it also allowed for like easier wiring because we could just put a hole in the center of our turret. Okay, so now I'll be talking more about the bearing stack turret. So in the bearing stack turret essentially makes a bearing sandwich. So there's first a thrust bearing at the top, a radial bearing in the middle, and a thrust bearing at the bottom. So the reason we have this is because the thrust bearings want to take like axial load. That means like all the forces like coming down. So it wants to be easier to spin on that. And then the radial bearing in the middle is allows the turret to spin along the groove. So if we go back to the previous slide, you can see like there's a huge cutout in this aluminum plate, and the radial bearings would spin on the insides, allowing like the turning motion of our turret. And we had a total of 6 stacks of bearings, and this was just a preference that we thought of, and it worked well for the entire season. And 6 of these allow us to like spin on the inside. And we can run a 6 mm go build a standoff in the middle in order to like make support of these, and it makes it easy to maintain since you can thread into the standoffs if you want to like replace the turret or replace any of the bearings. So these are just some specifications for our turret. So for the thrust bearings, we use the Go Build a 6 mm ID and 14 mm OD. And the radial bearings, we use this link for the bearing off Amazon, which I can send the link to the slideshow. We also used the Go Build a 6 mm outer diameter standoffs, and the length is dependent on the design needs. So we just chose the length depending on how tall we wanted our turret to be, or if we wanted like any like space underneath for like accessibility. For the large pulley and the small pulley, these are like very dependent on your robot. We just went based on our like sizing limitations and adjusted the motor RPM. So we ended up using a 182 pulley, which is HDT5 for the larger pulley. And for the smaller pulley, we used a 22 HDT5. Both of these pulleys were 3D printed, and we ran it with a 9 mm belt. And we ran a 435 RPM motor powering. We didn't really optimize the ratio on this pulley because we were limited by size constraints, but I highly recommend that you actually adjust the or optimize the gear ratios for each of the pulleys. And then for the motor powering, we we tried like both 312, 435, and 1150. And the 1150 RPM motor had too less torque to turn our entire turret, and the 312 was too slow. So the 435 RPM was like a nice meet in the middle for our robot and turning the entire turret. We also had like a lot of weight on top of our turret, so that's one thing you need to consider because we had 7 servos and 3 motors, and then we also had like 10 sets of Masumi slides. So that's why we needed such like a high torque in order to like turn this entire turret. So now I'll be talking about powering the turret. There are 3 main ways that we found to power the turret. The first is using pulleys and belts. So that's the one we were using for our Into the Deep season last year. And then 2 other ways that we thought of powering the turret was using a chain and sprocket, and then using gears, which is what we decided to do for our robot this year. So for the chain, it's like very similar to the belt. You could just use a gear, or you don't actually need this gear, but we just put it in like one of our prototype designs. And then from this gear, you can just run a chain across like both of these sprockets, and it works really similar to a belt. And then for the belt, last year we first had a bevel transmission in order to get the 90-degree bend so that we could set our U channel at the front of our robot. Sorry. And then we had a smaller pulley, as I was saying, this is a 20-tooth pulley, and then a 180-tooth pulley in the center. So this allows us to get the power transmission. One thing that we would change from last year, if we could do this again, was removing the bevels because this caused a lot of backlash in our turret, and it was not that like precise because we were using the motor encoder in the turret, and we would like remove these bevels so that we could just directly go to the pulley. And then one more thing about actually localizing the turret, there are like many different ways that teams do it. We actually like later on through the season, like towards the end, we put an absolute encoder on the on top of this axle so that we could like get rid of like the turret of the bevel gear backlash. And then if we put an absolute encoder, this will allow us to like home the turret more precisely. Another way that we thought of it and we saw other teams do this year is you can put like a small like extrusion out of the turret, and then you can put like a brake beam sensor or a color sensor, or like some teams use like a magnetic sensor in order to actually home the turret. So when it turns and passes over that point, you would know like the reset position of that of the turret or like wherever it's being headed. And then why we chose like the belt slash pulley, like we didn't see much difference between the mechanisms, especially from running like a geared turret this year. We were more experienced with pulleys and belts, so that's why we decided to use the pulleys. And we also found it easier to tension since the C to C of our turret wasn't perfect, and we had to add a few tensioners so that the teeth in our pulley wouldn't skip. And then it was also very easy to 3D print a large pulley. So we could just like 3D print this entire pulley in one go, and then also 3D print the smaller pulley. And most of the turret was done other than the off-the-shelf parts from the bearings and the standoffs. And then the main thing about turrets last year was having the right tolerance. So there's no actual right amount of tolerance because it depends on where you like cut your metal from, like how you prototype it, if there are any like if there's anything like wrong with your design, like you catted it wrong or found the wrong distance. So one thing we did to actually solve that before we ordered our full robot out of aluminum is that we would first laser cut our entire robot out of MDF because we have an in-house laser cutter, and we would find like around like what right tolerance we had. We had to go through like 3 different versions of this plate because our tolerances were pretty off. And then afterwards, we would then send it to FabWorks, and we actually didn't put any tolerance on the FabWorks order, and it came out fine. So that's how we got like the right tolerance for our turret. But like laser cutting did have a bigger improvement because originally like we made some errors in our CAD, and it turned out to be like a few off, and that like caused a big difference because our turret was shaking around a lot and the belt was becoming loose and tense because the turret couldn't be stable in one location. So laser cutting it could really help. The only problem with the laser cut turret is that you want like the plate for the turret, like this plate over here, to be very rigid. So that's why we chose to make it out of 3mm aluminum. We tried both MDF, carbon fiber, and aluminum, and we found aluminum was the best because the carbon fiber and the MDF, they flex too much to actually be rigid for the turret. And you want this plate to be very rigid because this is where the bearings are rotating around. And on top of the turret, we also chose to like have an aluminum plate because we thought it would be more rigid. And the rest of the robot, if you see our picture from our very first slide, was made out of carbon fiber so that we could be like very light for the level 3 ascent. So now we're going to be talking about wiring the turret. So there are like many different ways to wire a turret, but last year, because there was no like game element that was passing through the center of the turret, it made wiring a lot easier. So we could just run all our wires for our robot. We had like over 7 servos and 3 motors, and we could run all of these through the center of the turret. So what this allows us to do is that we could spin our turret more than like 180 or like or I think we like limited ourselves to like 270 degrees, so we could do like a full 360, but we could actually do more. The only reason we limited our turret to 360 degrees is because the more you keep spinning in one rotation, the more tangled your wires are going to get in the middle, and that caused a lot of like stress and disconnection since we had connections in the middle of our turret. So we decided to limit ourselves to 270 degrees so that we like didn't have to like rotate more than we need to. So some solutions to if you were to wire your turret through the center when there are no game elements passing through like last season is to use a slip ring. We actually tried using this last year but it became unfeasible because we had way too many servos and motors. And what a slip ring allows you to do is that it's just a device that in which you can like turn the end as much as you want, and essentially the wires won't get tangled. And the reason this is really good because you can continuously spin your turret like past like 360 or like even more like multiple rotations at a time, and your wires won't get tangled, and it'll just be a lot easier to wire, and you don't have to worry about like disconnections or anything like that. The only time this doesn't become feasible is when you have like a large amount of servos and motors, because you would have to connect like each servo and motor, each wire of the servo and motor to the slip ring. So, and then you would also have to use like different like AWG sizes depending on if you're using a motor or servo. And we had like over 7 servos, so that was like 21 wires. And we tried using a slip ring and we just couldn't like get that many wires through it without taking too much space in the center. So we just decided to put a hole in the center and then run like all our wires through. And now I'll be talking about how to wire you don't have if you don't have if you have a game element that's running through the center. So like this season, a lot of like people who are using turrets will have like the artifacts going through the center of their robot. So this is just an image of Theseus, which I saw had like a really like unique wiring solution. So there are two main ways that you can like wire a turret if you were to do it from the outside when you don't have wires passing through the inside, is using like a cable chain or a badge attractor. So what this allows you to do is have like a really nice guide for the chain. So as you can see, like the cable chain like wraps around, and they can like rotate their entire turret like I think up to like 360 degrees or maybe a little bit less, and then like rotate it back around when they need to. The only downside to this is that you can do multiple rotations because you're physically limited by the wires. So that's one thing you need to consider when doing software. One solution that our team found to this, because we ran into the same issue, was having wraparound logic. So once it like turns like 360 degrees and then it physically can't go, and your robot is continuously turning, you can just wrap around to the other side really quickly. So that's why you see a lot of teams that like their turrets do like full 360s in the middle of the match. That's just to deal with the wraparound. But this won't allow you to do more than like 360 degrees of rotations at a time because it'll stretch the wire and then it'll just get hardware limited by the cable chain. Another idea, if anyone's heard of this, is like badge attractors. So we actually use this on our Into the Deep robot, like not on the turret, but on the slides. So I'll just go back to the plan. So if you see over here, we had like these badge attractors over here, and they would like hold in our wires so that when our slides would extend, the wires could extend too, but when they come back down, they get like held in a loop over here. So that's like one unique way that you could like wire your turret or actually any moving mechanism. We have a lot of these battery tractors, and whenever we have like wires that are like hanging around, we make sure to like tie them back in so that they're like nice and compact when our robot's not extended, but they also allow like our turret and our slides to be extended like during the match. And So yeah, that's it for our presentation. If you have any questions, you can ask them here or you can email us at mechamantises@gmail.com. Thank you.
We can continue with Team Curiosity.
Awesome. Thank you. Can you see my screen?
Yeah, now I can see your screen.
Awesome. Sorry guys about that. Thank you. Okay.
So hello everybody. We are Team Curiosity 11770 from Los Angeles, California, and we go to Marlborough School. So we are so excited to be presenting on the engineering portfolio today. If you have any question at any time during the presentation, please write them down or put them in the chat and we'll be answering them after the presentation.
So first of all, you might be asking, who are we? We're a robotics team of women and gender minorities from Marlborough School in Los Angeles. Inspired by our namesake, the Curiosity Mars rover, we believe in making an impact through exploration, innovation, and most of all, collaboration. We were given the first place Divisional Inspire Award at the World Championships in the Into the Deep season, which is given to teams that best share their experiences, enthusiasm, and knowledge with other teams, sponsors, their community, and the judges. We also have our other past awards listed up on the screen. In this presentation, we'll be focusing on our experience creating an engineering portfolio and our advice for success. In the last few seasons, teams were asked to create a 15-page engineering portfolio to exhibit the important parts of their season. We'll talk about the guiding principles we followed when creating our engineering portfolio and some tips and tricks for creating yours in the future. And although the portfolio as of this season is no longer mandatory, we still recommend creating one so you're able to encapsulate your team and all the hard work you put into the season.
Before we get into some specific features of what we believe makes a good engineering portfolio, we advise you to check the game manual for an updated list of portfolio requirements, and you can come back to those requirements throughout the year. For some other advice, make the engineering portfolio a priority and start well before the deadline. Since you have a maximum of 15 pages for content, it can be easy to push it off until the last minute, but a good portfolio requires a lot of time to create quality content and showcase that content in a visually appealing way. We started working on our engineering portfolio nearly a whole month before our qualifying tournament, which gave us enough time to explore different ideas and complete numerous thoughtful revisions. Second, making the engineering portfolio should be a collaborative process. Since it's only 15 pages, there is a temptation to have only a few people work on it, but having all members from all areas of the team work on the portfolio is beneficial because it makes it so much technically stronger since team members can go in more depth about their specific areas of expertise. Additionally, having multiple people work on and revise every page helps you make sure that there are little to no errors or oversights. Finally, keep in mind that your engineering portfolio, much like your robot, should always be improving. We made many changes to our portfolio from our qualifying tournament to right before the World Championship based on our feedback we received from judges and mentors, which was integral to our success.
When it comes to designing and making your portfolio, there are lots of tools we use and recommend. Our team uses a shared Google Doc for planning and documenting our day-to-day engineering processes. We created our actual portfolio in a portrait-oriented Google slide. You might think of Google Slides as being boring, but it actually has a lot of fun and unique features that can be used to create an aesthetically pleasing and organized portfolio. Shapes, text boxes, the ability to collaborate, and the ability to import photos made design simple. And there are many tutorials that show more advanced tools as well. We also took inspiration from Canva to make the design look clean and aesthetically pleasing.
To start, we recommend planning out the overall structure of your portfolio by choosing a topic for each of the 15 pages. While this plan can evolve, starting with a general framework makes your portfolio flow well and convey an overarching story. As you can see in our outline, we explicitly touch on content for the different judged awards. For example, the outreach awards correspond to our 2 outreach pages. While you don't want to explicitly title your pages after each judged award, it is important to remember that your portfolio plays a key role in judging, since the judges are looking for information regarding a specific award when reading your portfolio. You should make it as easy as possible for them to find relevant information. And I know this year, a lot of the awards have changed and there are different elements to this year's game. So editing this is a good structure, but editing it a little bit will be helpful for this season.
In terms of introducing your team, we recommend including a team mission statement, highlights and lessons learned from the season, and some fun photos of your team in action. The team mission statement provides a way for you to state the team's purpose and values so the judges can get a concise, uplifting snapshot of who you are. We believe highlights and lessons learned are good for getting the judges' attention and telling them what is most important and how you've grown over the season. The portfolio should document your team's journey, so highlighting growth is very valuable.
And creating goals at the beginning of the year is a really good practice as it creates a baseline for the rest of the season. You can make goals for the team as a whole, outreach, and specific subsystems of the robot. You can write them down on a team plan page or another goal stating section. All goals are valid, just make sure everyone on your team is on the same page and you're working towards them together. Down below, we have some examples of goals that we set in Fright Frenzy for a specific mechanism.
For the outreach slides, you want to showcase the mentors you connected with that impacted you and the impact you had on your community. Including lots of pictures, especially of in-person events, is a really great way to convey your outreach. Don't just talk about what you did, highlight the impact you had and why it's important. Also, highlight your lessons learned from your mentors and especially how what you learned impacted your robot design, code, or how you work together throughout the season.
Let's get into some more tangible content you can include in your portfolio. You want your portfolio to showcase your design process throughout the season. Tying images into every page creates a more visual and detailed story. Early mechanism concept sketches, multi-view drawings, prototypes, and CAD model screenshots can help judges understand what you did during the season. It's also helpful to provide a small description of each image so judges know what they're looking at.
Sorry, my window just disappeared. The design process. So the portfolio is a crucial tool in communicating your design process to the judges. Robot-specific pages of the portfolio should thoroughly document the design process, making it very clear how you got to and from the initial idea to the final iteration of a mechanism. There are a few important aspects of the design process. What do you guys think it means for a design process to be silical? Pretty much, this is just making sure something is repeatedly being revised and making it so the original design isn't the final one, just kind of continuously iterating through it. So the design process should be based on your team's goals, which the portfolio should be centered around. So we'll go over the actual design process that our team follows.
As you can see on the right, here's an example of the design process. We begin by asking questions, researching solutions, and imagining possibilities. Next, we plan and create both through CAD and in real life, then go on to test what we've created and improve upon that. Finally, the design process loops back to asking more questions. This should continue in an iterative loop for each of your subsystems. Are two mechanisms not working together? Are you struggling with programming? Keep researching, trying solutions, and improving. You should document this process in the portfolio while keeping in mind your team's goals.
We don't come up with our mechanism ideas in a vacuum. Research is really important and helpful. We found a lot of other robots on YouTube and try to ask other teams lots of questions. If you found significant inspiration from another team's design, it's important to list that in your portfolio to be a gracious professional. As well as including images of the physical aspects of your robot, you should also provide explanations and evaluations of them. For example, in the planning of a robot arm, you could show a calculation of its torque, a chart of the design's pros and cons, and some data about how often it succeeds or fails at its goal in the game.
Although the regular engineering notebook is no longer required, it is important to maintain that level of documentation to make sure you have the material you need to create a thorough and accurate portfolio. Timelines and other detail-heavy features are also great for illustrating your process, so writing down dates and milestones will be useful for keeping track of for later.
One method that is very helpful is to split pages up by mechanism. On a subsystem page, it's good to provide a clear overview of the mechanism, conveying to judges what it does and its importance. Next, highlight any important drawings or CAD iterations of the subsystem. Including these types of images really give the judges a good idea of your design process and how you settled on your final design. Be sure to include a timeline and any significant milestones, such as completing a new iteration, as seen here with our claw. Include other technical details like calculations you did in the process of making your mechanism, in addition to what you learned from those calculations. We included a section about our use of sensors and intelligent control on each page. We also included a lessons learned section to demonstrate the growth of the mechanism and our team throughout the design process. We recommend making the format of different subsystem pages very similar for the sake of consistency. For example, all of our subsystem slides had an overview, lessons learned, functional requirements, intelligent control, and a picture of the subsystem that explain the basic function of the mechanism.
Try to strike a balance between being concise and being detailed. No judge wants to read 15 pages of tiny text, but they also want to have enough information to figure out what you did this season. Add clear headers that show your judges what is most important. We think that this screenshot from our team scoring element shows off this very well. We also played with font, text color, size, and bolding throughout the notebook, and ultimately decided to bold and change the color of the most important concepts. Play around to see what is clearest and looks best in your portfolio. In addition, we added lots of images to show off the evolution of our team scoring element and its CAD models, while also adding a description of the major changes we made at each step and emphasizing keywords and concepts. As seen on both this slide and the last slide, we put a lot of dates in the portfolio to show our continual revision process.
Aesthetic appeal is an overlooked aspect of the portfolio. It can be great to build a theme for your portfolio. Make space for your titles, stay consistent in logo placement, and keep a standard orientation for your text. One of the major things you can pull your portfolio together is a color scheme. As you can see in our presentation images of our portfolio, our color scheme is a variety of reds, some yellows, and a couple of grays. When making a color scheme, make sure that all the colors are readable first and pleasing to the eye second. Using all neons might not be the best idea. Add fun and simple embellishments and experiment with transparency and shapes. Notice the timeline arrows in each of our mechanism pages, as well as the lessons learned boxes at the bottom of this page. These features subtly stand out and create a theme between pages, but don't draw attention away from the content.
If there's one thing that you should take away from this presentation, it's that your portfolio should always tell a story. This applies to the notebook overall as well as individual pages. The judges aren't expecting you to include every little detail, but making sure that your portfolio has a clear flow from start to finish is essential. Every team has a different strategy and a set of goals, so each portfolio will be unique. Here you can see what our design process slides look like. The image-heavy timeline helped us display the overall story of our season.
Last, but certainly not least, be yourself. These judges see dozens of teams a day, and you want to stand out. Stay professional throughout the process, but don't be afraid to have fun with your portfolio and be creative about how you present your team. Pick a fun color, font, and layout theme that you think represents your team and stick with it. Throughout our portfolio, we sprinkled lots of fun images and inside jokes, many of which we believe contributed to our success throughout our seasons.
Now, with everything you've learned, do you have any suggestions about how to improve this sample? Oh, did we change that one?
I think we're going to skip that slide. That's okay.
Okay, perfect. If you have any questions, feel free to ask now. We'd love to hear any thoughts, comments, or anything else you have as well.
Also, our teams opened up portfolio feedback after winning the Think Award during Center Stage at Worlds. So we also have examples of our portfolio back on our website, but if you'd like to send in your portfolio, we found it helpful to give specific feedback to teams that request it and extend the advice and knowledge we've learned when perfecting a portfolio. We can give you 2 to 3 pages of detailed suggestions, and if you'd like a Zoom meeting or if you'd like to receive feedback on any past portfolios, you can scan this QR code. It's also available on our websites and all of our social media, as well as all the portfolios are at this link. So thank you guys so much for listening, and if you have any more questions, feel free to contact us at Curiosity11770 on Instagram or by emailing us. And you're welcome to check out either of our websites. So thank you so much. My first kind of thing was you want to make sure you have at least some content for every single kind of aspect of the awards. So you want to make sure you have at least 1 or 2 outreach pages, but you also want to use your portfolio to play into your strengths as a team. So if you're a very technical team, you really want to make sure you're using the majority of your pages to talk about your technical strengths. And similarly, if you're very strong on the outreach side, you definitely want to dedicate a couple more pages to that. So really optimizing your pages based on your own team strength is something we would definitely emphasize. And then between balancing it, just trying to make sure that you're hitting all the goals and talking about everything you did this season, kind of the most detailed extent you can get to without really kind of flowing any pages would be my advice.
If none has any more questions, I guess we can finish with Team Rev Amped.
Okay. So we are Team Revamped Robotics from Portland, Oregon. I am Tanner. I'm the mechanical lead. I think I'm the only one in this meeting right now because my teammates are sleeping. But we're going to talk about our intake from last year into the deep. We had a pretty complex intake. In general, the robot was very complex, but we found ways to make the complexity still be reliable. So this presentation is kind of going to talk about how we balanced the complexity of the intake with reliability so that things don't break. So this is the intake itself. This was the intake that we ended up using at the World Competition and at the Maryland Tech Invitational. Obviously, it looks pretty complicated, but it's basically using a very typical intake, which a lot of teams have here, which was just some noodles. This is kind of the standard active intake for the deep. Tons of teams were using this. And then we also added the coaxial virtual floor bot. And that allows us to have a lot more degrees of freedom. So this was something we did when we redesigned our robot for the World Competition. And we did this for a couple of reasons, which I'll talk about a little bit later. But basically, it gives us flexibility so we could intake in different ways in the submersible. And also, because our deposition was complicated, it ended up giving us more areas to intake without needing to extend our horizontal extension. And with like the extension limits of last year, that was something that we had to consider in our design a lot. We also had a continuous pass-through. So this trap door here was on the servo. And if this opened, we can continuously intake straight through. And that made our intaking a lot faster. And this was kind of needed with the virtual floor bar because the standard drop down, this would jam or would hit something and you can't really go as fast. And then also it allows us to transfer vertically. So I'll have an image demonstrating that a little bit later, but the vertical transfer allows us to basically make our transfer a lot smaller, and that allowed us to compact the overall size of our robot because our redesigned robot was almost like, I think, 2 inches shorter than the first one we had. So that helps just for like driving, and we got lighter and things like that. That's in general going to be kind of more optimized. But obviously with this functionality that we added, it introduces a lot of complexity. It introduces failure points. So we had to do a lot of things for solving that. So this is the intake positions I was talking about. There were 3 main ones. We have the normal intake, and this just is kind of standard. This would be how we would intake most of the time when we're just going as fast as possible. And the intake's just touching the ground. The noodles are almost at the ground. And we can intake pretty nicely this way. And then we also have a vertical position where the submersible had a barrier around the edge, and sometimes samples would get like up against that barrier, and most teams cannot intake that. So we were able to lift it up, point the intake down, and that gives us the ability to intake a sample that might be stuck on the wall of the submersible. And then finally, this one here, that is our vertical transfer position. So this is how we will actually like transfer the samples from our intake to our deposition, which is just good for size. Obviously, this is a lot smaller than a lot of other designs. It may be slightly taller, but that wasn't really an issue for the way we packaged our robot. And in general, this was definitely something that took a lot of iterations because the vertical transfer is kind of an issue, especially you're fighting gravity with the samples. But we had ways to solve that. Going back to this page, we have, hard to see here, but there's a compliant flap that will lock the sample in place at the top. And that allows us to turn the intake off without the sample falling out, which was really good for the transfer. Okay. And then, as I mentioned before, we did a full robot redesign going into the World Championship last year. And so this was the intake for the original robot. This was the one that we used during our league meets and our state competition. And we actually won the state competition with this intake and the different robot. So this one is a more typical design for last year with the single drop down. It's just on a pivot. We had a much wider design originally for kind of make it easier for the drivers. And then we also had a larger transfer like box area with trap doors that would open that we could then, that was how we were able to reject samples that might have been the wrong color or something like that. But this was like a lot simpler. Definitely worked. It wasn't necessarily more consistent, but it was very consistent most of the time. Although one of the issues we had with this is because we were dropping it straight down, it would sometimes get stuck on the sample, and then we'd have to move around a little bit. It was also just bigger and heavier, which means it's more strain for the servos, and it's also just makes our robot heavier in general. And then also, since it's on the end of the extending horizontal slides, that can cause kind of a cantilever effect on the slides, which may bend them, have issues there. It didn't really ever have that issue, but it might have if it was heavy enough. The main benefits of this was the transfer was really consistent because the sample was always in the exact same place, and we never really had any issues with like samples falling out or anything like that. Although it did have a slightly higher rate of jamming from our the redesigned version because it was so big, it could intake multiple samples at once. So that was definitely something we were able to mostly avoid that in this design through some software solutions where we were able to automatically reverse the intake to clear it whenever we had gotten one we wanted, and things like that. But then, so the key differences between the two designs, and this is really what I want to highlight for the presentation, is obviously this design has a lot more degrees of freedom. We have the coaxial virtual 4-bar, which is how we actuate the intake, but that adds failure points. We also swapped a lot of things from the original version, which we should have probably tested more, and that caused problems at the World Championship with inconsistencies that we had not foreseen because we had just not done enough testing. So like a smaller intake area, which obviously makes it slightly harder for the drivers, although it added accuracy, which was definitely ended up being like a net positive. That accuracy made a huge difference for our autonomous mainly. It allowed us to get more cycles in and less likely to have like jams or intaking the opposing alliance's color, which was definitely a problem last year with like penalties and all that. We also had changed the packaging entirely. So we have now, instead of like everything being packaged on the intake, there's bare motor packaging. We have multiple servos here for actuating the 4-bar, and then just like the whole structure ended up being more complex. And then pass through, which I mentioned before, but that was a major change with the vertical transfer and how we kind of worry about that whole thing. And then mainly creating reliable designs here. There was a lot of things that we should have done differently. And this is kind of what I want to talk about, like mainly highlighting testing everything as much as possible. We like using test beds, and this is something we're really doing this season, is every design is being put on a test bed and tested thoroughly before it is even like put on the robot or we even think about running it at a competition, because we need to know all of the points it's going to fail. And if those points of failure end up being too much to kind of deal with, or we can't solve them, or especially if they break the robot for the whole match, that's a huge issue. So we had a couple of those. And so some of the examples, aside from in general, like not testing enough, and with changing bare motor, this was the first time we'd ever used bare motors before. So this was a huge change for us. The other thing we did a lot here, because we weren't, the packaging was not as efficient, was like long gear trains. You can see up here, this servo here, this axon, is what's actuating the first stage of our virtual 4-bar. But it has a 3-stage gear train just to transfer the rotational power down to the arm. And this adds a lot of backlash into the design. And it ended up being where this arm could be anywhere plus or minus 10 degrees, which was a real big issue for transfer since we have so little room for error. Like going back to here, this pretty much has to be perfectly vertical or the claw is going to miss and we're not going to be able to intake, or we're not going to be able to transfer. And we definitely saw this when if the arm was too far forward, the claw would grab the back of the intake, or the claw would overshoot and it would slam into it, and that could break things. We also had the similar issue here with the bare motor reduction, where we had this press fit bare motor gear and then 2 stages of gearing, which wasn't quite as big an issue because the backlash is irrelevant with the active intake. Although with the bare motor, one of the issues we found was at one of our competitions, the gear came off the motor and it was almost impossible to get it back on. And that caused some serious issues for a couple of our qualification matches until eventually we were able to fix it in between the qualification and the playoffs. But that was something that we definitely could have known was an issue if we had done sufficient testing. Additionally, for bare motors specifically, I think I would recommend trying belt reductions as well. The gearing reduction was not ideal. It wasn't very efficient, and the gears on our bare motor at least did not seem to mesh as well as we wanted with the normal Go Builda gears. Not quite sure why, because they're supposed to be the same, but it's possible we just had like bad gears. I'm not quite sure, but either way, now this season everything we're using is the hex axle, and then we'll just do like, the normal like pulleys or whatever for belt reductions and stuff. Oh, and then another one here, and these are kind of all things that just require a lot of testing and learning through mistakes, I would say, is we had both of these servos here, this one at the bottom, which is the second stage of our virtual 4-bar, and then also the top one, we have the screw, the set screw for the servo is actually what's like connecting these connector beams. And what we found was because this is moving, it would unscrew the screws on both of these. And for this one, this was a really big issue because as it unscrewed throughout the match, it would actually block this beam here. And then we could not transfer at all. And that ended up like being a really big reliability issue, because if that ever happened, it just completely breaks the robot for the rest of the match. And that's just not something we can really feasibly do. So one of the things we did actually in the off season, so this was the intake we had up until all of our competitions last season. But after the last competition, the Maryland Tech Invitational, we kind of wanted to see what we could have done different. So this here is a top view of the design we had at the Maryland Tech Invitational. And it's obviously pretty cluttered. I don't know, it looks a little complex here. This was the design that we not swapped to, but this is one we designed afterwards to see how we could have done it differently. And the second design was a lot simpler. As you can see, there's no long geared trains. Everything is a single stage reduction. The bare motor has one gearing. Both of these servos have one gearing. We also managed to fit all of this inside, so we didn't need the servo above our horizontal slides like this. That got a lot simpler, and we were even able to fit one of the rev servo hubs for wiring. And this is just a lot nicer. Definitely something that this kind of design could have definitely been made for our season if we had gone through more iterations. But again, that comes back to like what I was saying about really testing all your designs and making sure you put your designs through a lot of like rigorous iterations just to kind of find problems like this and then find solutions. And one of the things similar to what Seattle Solvers was talking about earlier is master sketches are really good. And we did top view sketches for this that outlined all the components. And that's how we were able to find out that this packaging was viable. Whereas here, we definitely did a little bit, but we just didn't try enough versions to where we never figured out how to fit everything in the nicest way possible. So multiple iterations has really helped us balance the complexity of our designs and then also make them reliable. And that's something we're taking into this season as well with I mean, right now we've already been through, I think, 8 or 9 different intake versions, whereas last season this was only our fourth complete version. So just even the number of versions that we've gone through has been really good. That's kind of all I have. So thank you for listening. If you have questions, you can put them in the chat or email us at revampedrobotics@gmail.com, or just reach out to anybody on the team through Discord and we can answer your questions.
If no one has any questions, thank you for joining today's conference. Thank you for the presentations. I've seen amazing presentations today, and see you tomorrow at 1 a.m. UTC.